In the last class, we understood the functioning of a bipolar junction transistor as an active device, and we took for our illustration a PNP transistor like this, and we explained how the collected current is almost nearly the emitter current. Now, for the PNP transistor, the symbol, instead of drawing it like this, the symbol for the PNP transistor is as shown here. Here, the direction of the arrow is put at the emitter. The direction of the arrow always indicates the direction of actual flow of current. Here, if this is forward biased, emitter base junction is forward biased, the current in this is going to be injected from the emitter onto the base, actual direction of flow of current, and therefore arrow is always put in the emitter, and the collector is this and the base is this. So, this kind of symbol indicates a PNP transistor. In the case of a NPN transistor, the arrow direction is opposite. Now, as far as the transistor action is concerned, emitter base junction is forward bias and the collector base junction is reverse biased, so as to make the entire collector current become equal to the emitter current, and alpha becomes very nearly equal to 1. That is the transistor action. Current in this is represented as total current as IE. Almost the entire current, that is emitter current, becomes part of the collector current. That is transistor action. That is facilitated by forward biasing base to emitter junction and doping emitter very heavily, making the base width very small, so that most of the injected carriers constitute the total current, and most of the injected carriers come to this part of the junction, and this distance is made so small that there is no recombination here, so that most of them arrive at this point junction, and here there is a field which is aiding them to get collected very fast because of the fact that it is reverse biased. So, IC is equal to alpha times IE, where alpha is very close to 1. In an ideal transistor, therefore alpha is equal to 1. So, which means almost all the current gets collected here, and therefore in the other terminal there is no current. Base current is 0 in the ideal transistor. In practice, alpha is typically of the order of 0.98, 0.99 typically. So, alpha is about 0.98. This is the order. So, it is pretty close to 1, please remember that. In IC transistors, it can be even made closer to 1 than this, okay, maybe 0.995, things like that. So, transistor action means IC is equal to IE, base current is 0. Actual current equation at this node, therefore, is emitter current is always equal to collector current plus we call this base current. So, this is Kirchhoff's law. This has nothing to do with transistor action. In this node, emitter current is always equal to collector current plus base current. What is transistor action is IC is equal to alpha times IE. In an ideal case, alpha is equal to 1 and IB is therefore equal to 0. Now, let us look at this its characteristic in a pictorial sense. Whatever be the base to collector voltage, reverse bias voltage, collector current is almost independent of the base to collector voltage. So, it is independent. It depends only on emitter current. If emitter current is 1 milliampere, for example, collector current is going to be very nearly 1 milliampere. So, this is emitter current, this third parameter. Okay. So, as emitter current is being varied, okay, how does collector current vary? Collector current remains constant at nearly 1 milliampere. If it is 2 milliamperes emitter current, the collector current remains constant, okay, independent of base to collector, okay, voltage, which is the reverse bias voltage in this. It remains constant at 3 milliamperes, it remains constant at 4 milliamperes. Now, strictly speaking, beyond this point, this is the point where VBC is equal to 0. Okay. Beyond this point, the transistor is said to be in the saturation region, in this region. Suppose therefore, actually the current will start falling. So, this point is called saturation region. Beyond this point, okay, beyond this point, it is cut off. This is the active region. This region is called the active region, where transistor action takes place, where the relationship IC is equal to IE, or IC is equal to alpha times IE is valid. Now, therefore, we just say VCB equal to 0 is the borderline separating saturation and active region, and IE equal to 0 is the borderline separating cutoff and active region. Once again, let us consider the other regions. If collector base junction is reverse biased, emitter base junction is forward biased, it is said to be in the active region. If emitter base junction is reverse biased and collector base junction is reverse biased, it is said to be in the cutoff region. So, VEB, okay, emitter base junction reverse bias, collector base junction also reverse bias, the transistor is said to be in the cutoff region. Ideally speaking, you can therefore consider that these are two junction diodes which are reverse bias, and therefore they are all open, right. So, emitter base junction can be treated as open circuit, collector base junction can be treated as open circuit. So, this transistor is cut off. Then we have emitter base junction forward biased, and collector base junction also forward biased, the transistor is said to be in the saturation region, that is in this region. Transistor is said to be in the saturation region. Then there is another one, that is collector base junction forward biased, emitter base junction reverse bias. Transistor is said to be in the inverse mode, not normal mode, but is in the inverse mode. This is normal mode transistor action. And therefore, if collector base is forward biased, emitter base reverse biased, the transistor is in the inverse mode. In this, transistor action takes place exists, but alpha is not close to 1. It's not close to 1 because this transistor has been fabricated specially to work in this normal mode, right? If it is symmetric, if it had been PNP without any care for any special effect, okay, regarding highly doped emitter, etc., if it is just PNP and symmetric, then both could be normal modes. You can use emitter as collector and collector as emitter. In this case, it is not so. So please remember that the characteristic curve for the transistor can be easily obtained. You yourself can draw it, okay, without any hesitation once you know that IC is equal to alpha I. Therefore, it is not necessary, it is not important that we should keep pictorial view of this, okay. We can remember these equations very easily, and therefore, this is just done for this once, and we are not going to use this information again in our future analysis, okay. So this graphic way of representing the output characteristic of the transistor is going to be over with this, right. In further discussions, we will not use this. We will strictly use this information, okay. It is this information which can be easily pictorially represented. Now, as far as the non-ideality of the transistor is concerned, in the last class itself I have told you that alpha I is not equal to 1, IC is equal to alpha times IE. Not only that, a better approximation is, okay, IC is equal to alpha times IE plus IC naught, because this junction is reverse biased, okay. There is this reverse saturation current also flowing in addition to the injected current, okay. So this will add on to the collector current, and actual current is going to be alpha times the injected current, okay, plus IC naught. Now this equation can be normally used whenever we want fairly accurate information about the transistor, okay. Otherwise, in most of the applications, we can just use the information that alpha is equal to 1. That is going to simplify the analysis of any of these transistor circuits, particularly in situations where we have systems built with large number of transistors, okay, where we would like to only approximately analyze the circuit, and therefore would like to quickly arrive at the results, in which case the easiest approximation for the transistor is alpha is equal to 1. Now, with alpha equal to 1, we have shown that IB is equal to 0. Now look at this structure. IB is 0, alpha equal to 1, because of that IB is 0, and emitter base junction is forward biased, which means VEB ideally should be equal to 0. If it is an ideal diode, emitter base, okay, if it is replaced by ideal diode drop, will be 0. Otherwise, it is 0.5 to 0.7 volts. So ideally speaking, VEB is equal to 0, okay, if it is an ideal diode approximation, and IB is equal to 0. So you can see here that at the input VEB is going to be very nearly 0 and IB is going to be very nearly 0. This concept of input voltage 0 and this current being 0 can be represented later on by an equivalent element. This we will discuss later. But remember that input voltage is 0 and this current is 0, okay, in the case of an ideal transistor. Now, as far as output current is concerned, it can be always anything, but it is dependent upon the input current IE here. Okay. So, it is equal to IE, very nearly equal to IE, and it can flow into any resistance and develop any potential. So, you have any potential, okay, getting developed at this point, strictly speaking, ideally speaking. So, this is a source, dependent source. So, now let us consider the other type of transistor, NPN. So far we had discussed PNP transistor. So, the other type of transistor, NPN transistor, the transistor action again occurs according to the same condition, that base to emitter junction is forward biased and collector to base junction is reverse biased, but the polarities of voltages now will be the opposite. So, base is made positive with respect to emitter and collector is made positive with respect to base in order to achieve transistor action. So, the equations will remain the same, okay, as only the direction is going to be different. Now, emitter current is going to be, actual direction of current is indicated by the direction of the arrow. So, it is in this direction. So, the collector current is going towards the node and base current also will be towards the node, actual direction of current. So, the equation still is valid, IC, okay, plus IB is equal to IE. This is the Kirchhoff's law, this is still valid, okay. Only thing is emitter current is going away, okay, from the node, collector and base currents are going towards the node. So, that is the difference between NPN transistor and PNP transistor. Only the biasing is going to be different, okay. In the sense, bias voltages will be opposite to that of the earlier situation. But base to emitter junctions should still be forward biased and collector base junction should still be reverse biased. So, in future, in all our discussions, we will be only using these symbols for NPN and PNP transistors, and automatically please remember the arrow direction will show the actual direction of current flow in the circuit if it is biased properly. Now, let us consider this as a 3-terminal block. So, assume that this has been put inside a block. Supposed to be the amplifier block, okay. So, we have now a 3-terminal block available here. Let us put it slightly differently. So, this is the input port and that is the output port. We have had earlier general discussion about 2-port network and the 2 ports were independent. Here, one terminal is common to both input and output. So, this is actually a 3-terminal, okay, device, obviously, with input port, okay, and output port having emitter as common. In this case, in this device, we have input port and output port with emitter terminal as common terminal between input and output. So, we can call this a common emitter amplifier. The idea is this emitter terminal is common between input and output. So, we have a common emitter amplifier here. Let us now represent this, therefore, this way. The input voltage here Vi for this is same as VBE. The output voltage is same as VCE. Input current in this case so input voltage is equal to VBE, output voltage is equal to VCE. So, E is common, you can see. Input current is same as base current. You can look at this is the base current, and output current is same as collector current. You can write down this. This is IE emitter current, this is base current, this is collector current. So, in this common emitter amplifier, which is put inside an amplifier block, okay, we can now represent Vi, which we have earlier used for our two-port network. Here it is same as VBE. V0, which we have used in our two-port network, is same as VCE. II is same as IB. I0 is same as IC. Now, let us consider the ideal transistor situation. So, ideal transistor. In an ideal transistor, for the transistor action to take place, we must have this forward biased. So, this has to be forward biased. This junction has to be forward biased. And if it is an ideal diode, okay, the junction drop is 0. So, which means Vi is 0. So, in an ideal transistor, in this case, Vi is going to be very close to 0. In practice, it is about 0.5 to 0.6 volts. Okay. Please remember that in practice, it is a semiconductor diode and it has a cut-in voltage of about 0.5 to 0.6 volts. And II is going to be equal to 0 because ideal transistor alpha is equal to 1, okay. IC is equal to IE, and from our this thing IC, if it is equal to IE, IB is equal to 0 according to this. IC equal to IE, IB is equal to 0 automatically. That means this is the situation of the input for a common emitter amplifier. Vi is equal to 0, II is equal to 0. Then IC which is nothing but the I0, IC is equal to I0 is going to be equal to IE. Okay. So, this is the output volt current, and VCB, which is V0, can be anything, right? Any positive voltage. Okay. So, any voltage. V0 can be anything. That means, actually speaking, I can now represent this by means of an equivalent circuit, the simplest equivalent circuit. So, we will put down this transistor in terms of its equivalent. I now put here, okay, about what is called as some block here. What it says is, this is what is called as a nuller. What is a nuller? By definition, nuller is something which has current I through it equal to 0 and voltage across it equal to 0. Null, okay? Both are nulls. Current through it is equal to 0, that means it will not allow any current to flow through, and voltage across it is equal to 0. So this is called a nuller. And here I put a source which is to say that this current has to flow through this, right? So this source is something that can deliver any amount of power, that means any voltage or any current depending upon what is applied here, okay? So this is called a narrator. I is anything, V is anything. This is called a narrator. So an ideal transistor, therefore, is a combination of nullator and narrator with a junction between nullator and narrator. This is the simplest equivalent circuit in terms of networks for a transistor. Is this clear? Another thing I have to tell you is, this nuller is I equal to 0, V equal to 0, and narrator is something with I anything and V anything. This concept can be made clear by defining an equivalent for simplest things that are possible in electrical engineering. This is a short circuit and an open circuit. Let us therefore find out the equivalent for a short circuit in terms of nullators and narrators. Right? What is a short circuit by definition? Short circuit is something like this, let's say. Here the voltage is 0 and current is anything, not defined. Okay? Current can be anything. That is called a short circuit. What is an open circuit? For an open circuit, the current is 0, current through the open circuit is 0, but voltage can be anything. This voltage can be anything, whereas in a short circuit current can be anything but voltage is equal to 0. Suppose therefore I want a nullator narrator equivalent for this, okay? It's very simple. I want a nullator narrator equivalent. Another thing, according to the theorem, nullators and narrators cannot occur individually. They always occur in pairs. For physical existence of these blocks, nullators and narrators occur in pair. Nullers and nuller or nullator it is called, occur in pairs. That means if there is a nuller, there should be a narrator corresponding to that somewhere in the network. Okay? They always occur in pairs. So, physically you cannot have only nuller existing or narrator existing. Okay? In which case equivalent circuit for a short circuit will be this is the equivalent circuit for a short circuit. So that this nuller makes the voltage 0. This narrator will permit any current to flow through. Okay? So this nuller will make the voltage 0 and this will permit any current. So effectively you have a short circuit. More importantly, right, we can have an open circuit. Okay, in series. Okay, this will prevent, okay, the current to flow. So this will make the current equal to 0. So nuller will come in series. It will make the current equal to 0, and therefore since this is coming in series, the voltage here can be anything because of the narrator. The voltage across this is 0. The voltage here can be anything. So voltage can be anything. Okay, current is 0, which is an open circuit. So this two are equivalents in terms of nullite and narrators for short circuit and open circuit. Now for the transistor, what is the equivalent? Nullator and narrator will occur in pair, and this end is the collector, this end is the base, and this is the emitter. The junction point of nullator and narrator is the emitter. So if you have in a network, okay, nullator and narrator forming a junction, such a network can be realized using transistors. That is, if you have a nullator narrator formulating a junction, such a network can be used using realized using transistors. If you don't have such a junction, then we can formulate a junction by using these open circuits. Okay, open circuit, putting an open circuit will not disturb any circuit. Okay, so by putting an open circuit, we can introduce junctions and realize the bipolar transistor versions of the same network. So please remember that we have evaluated from the NPN transistor. For that matter, we could have started with PNP as well. We would have arrived at the same equivalent. As far as equivalent circuit is concerned, whether it is NPN or PNP transistor, the same equivalent circuit is valid. Okay. Now only thing is that the initial voltage in these cases, we said ideal cases it is going to be 0, and practically we must have this going positive. In the case of the PNP, it will have to go negative. That's all. So as far as the equivalent circuit of a transistor in its simplest form is concerned, we can say that for a common emitter amplifier, the nullator comes in series at the input and narrator comes in series at the output, and the nullator narrator junction is common to both input and output, and that is the emitter. Okay. We had now discussed the 3-terminal device NPN transistor as a common emitter amplifier. Let us now consider how in practice this is biased. So with respect to emitter as common, let us consider the supply voltage is VCC positive. So, this is a positive supply voltage VCC. Then automatically this collector is going to be at a higher potential than the emitter, and it can be made as high as you please by selecting VCC. So, this VCC automatically reverse biases this and simultaneously forward biases this. So, by using a single supply, if you use emitter as common and put down your voltages, this will be automatically plus minus and plus minus. Even if you keep this base open, the junction, these two junctions come in series with one another. So, one junction will automatically get forward bias, that is emitter base junction. The other one, collector base junction, will automatically get reverse bias. The forward bias junction will take a voltage of about 0.5 to 0.6. The rest of it has to come across the collector base junction, which is adequate for reverse biasing it. Okay. So, this is called a single supply biasing of a transistor. Now, basically, if I keep this base open, what will happen? Let us see. If the base is open, collector base is reverse biased, emitter base is forward biased. In this arrangement, that means transistor action should take place. Transistor action takes place. Okay. What is transistor action? Transistor action is IC equals alpha times IE plus IC naught. This is valid. And one thing else also is valid. Base is open, so base current is 0. So, according to Kirchhoff's law, IB is 0, therefore, IC has to be equal to what? IE, because this current has to be equal to this current. If that is the case, then you have very interesting thing happening here. Okay? Under this kind of biasing arrangement, we have IC equal to IE, so replace it there. IC equals alpha times IC plus IC naught, or IC equals IC into 1 minus alpha equals IC naught, or IC equals IC naught by 1 minus alpha. So, there is a collector current now flowing, even though base is open, there is a collector current flowing because of the leakage current, which is IC naught. Not only that, that is amplified by an extent of 1 by 1 minus alpha. Alpha is close to 1. So, this factor 1 by 1 minus alpha is going to be much greater than 1, and therefore, this leakage current under this situation of biasing is going to be more than IC naught. If IC naught is of the order of nanoamperes, this might come under the range of hundreds of nanoamperes. So, anyway, we are going to ignore the effect of IC naught. It is still very small, and therefore, we can assume that there is almost no current flowing. IC equal to IC naught by 1 minus alpha, that we remember, but it is going very small, and therefore, the voltage here is going to be very nearly VCC, or actually the voltage is VCC, strictly speaking, minus IC into RC. This is the voltage VCE. This voltage VCE is going to be VCC minus IC times RC. This is nothing but V naught always. Okay? So, this equation is always valid. Another equation is Vi equals VBE in this case for this circuit. So, now we can find out, okay, the effect of this is, let us say, II. The relationship between Vi and, let us say, IE, this is IE, is known, okay, because IE is equal to IE naught exponent, okay, VBE by eta Vt. Minus 1 we will ignore, so it is approximately equal to this. This we know, okay, or I will put it as equal to minus 1 approximately equal to IE naught exponent VBE by eta Vt. Let us assume eta to be equal to 1. We have said eta is between 1 and 2, right. So, IE is equal to IE naught exponent VBE by Vt. This is equal to IE naught exponent VBE is same as Vi. So, we have IE, and what is IC? IC equal to alpha times IE plus what? IC naught. This IC naught I am neglecting now. So, equal to alpha times IE naught exponent Vi by Vt. Or now V naught is going to be equal to VCC minus, already we have now IC in terms of Vi. So, alpha times IE naught, okay, that into RC exponent Vi by Vt. This is the nonlinear relationship between V naught and Vi without making any approximation whatsoever, right, except that IE has been made equal to IE naught exponent VB by eta Vt, ignoring that one, because emitter base junction is always forward biased. This approximation can always be made, okay. So, this approximation in future will always be made, and I will not repeat it again. We will take it for granted that IE is equal to IE naught exponent VB by eta Vt in the case of transistors, okay, and also eta equal to 1 we will take unless otherwise mentioned, and in all future situations we will take IC as alpha times IE naught exponent Vi by Vt. And if you plot this, let us plot this. This will give you V naught versus Vi characteristics, okay, transfer characteristics for the amplifier. This is the common emitter amplifier, okay. So, NPN transistor inverter we will call it. We will see why it is called inverter presently. So, when this Vi is 0, when Vi is 0, this exponent is going to be e to power 0, which is 1, and alpha IE naught RC is the only drop, IE naught being, okay, of the order of nanoamperes. This voltage RC may be of the order of kiloamperes. This voltage may not be much, right. So, this can be ignored, or it is slightly less than VCC. So, it is going to start at very nearly VCC. because of the fact that for RC of the order of kilo ohms, IE naught of the order of nanoamperes, this voltage is going to be extremely small. VCC of the order of volts, let us say we are considering. So it is slightly less than VCC, and it will start with VI becoming substantial. What is substantial? VI is substantial when there is substantial current flow. That will happen when VB is of the order of 0.5 to 0.6. So when this voltage is of the order of 0.5 to 0.6, so this is therefore V naught, VI. This is of course V naught. So V naught will start with VCC, and when it is 0.5 to 0.6, let us say this is about 1 volt, this is 1.5 volts. Okay. So by about 0.6 or so, it will follow exponentially. Current is going to increase exponentially with input voltage. So the voltage will drop because this drop will increase. Right? This will keep on increasing very drastically. Keep on increasing. After a certain point, when this voltage keeps on decreasing, okay, a point will be reached when, if this is 0.5 to 0.6, let us say, and this is 0, it has reached saturation, because VCB equal to 0, we said the transistor has reached saturation. That means when VCE becomes about 0.5 to 0.6, it has just entered saturation. So any voltage which is less than, let us say, 0.6 or so, will make it go to saturation. This voltage is going to be extremely small. So out to this, it is going to be, the transistor will enter saturation somewhere here. Okay. So thereafter, both the junctions are going to be forward biased, and the transistor is deep in saturation. Okay. So this characteristic is that of the transistor inverter character. Why is it called inverter? You can now see that this is the active region. This point, okay, it might enter saturation. Beyond this point, this is in cutoff, right, almost. Oh, this is the active region. This is the active region. Now, in this region, you have to operate in order to make the transistor amplifier. The transistor should not enter saturation, that transistor should not be in the cutoff, it should be in the active region. If it is in the active region, it can work as an amplifier, and it will be linear only for small signal changes, because basically it is nonlinear, it is an exponential relationship. E to power Vi by Vt can be expanded as e to power x, okay, 1 plus x squared by factorial 2 plus x cubed by factorial 3, that way. So basically this is equal to VCC minus alpha IE naught RC into exponent x, okay, which is actually speaking exponent, let us call it as VI Q, some voltage which is constant, plus delta VI. That means I am changing the voltage by a small amount around a quiescent voltage. Okay. Why is this being done? Because this voltage can be increased or decreased. Okay. So I can apply an AC input by maintaining basically the emitter base junction at a quiescent voltage of VIQ. Okay. This effective voltage should always be of the order of 0.5 to 0.6. So this is going to be VCC minus alpha IE naught RC exponent VIQ by VT, VIQ by VT, right, into exponent delta VI by VT. What is small signal? Small signal is that signal at which I can consider this relationship between input and output linear. So, when the input voltage is changing by a small amount, then I can consider it as small signal. That small amount is comparable to Vt. Vt is of the order of 25 millivolts. That means, if this delta Vi is of the order of few millivolts, then it can be considered as small signal. Then we can expand this as 1 plus delta Vi by Vt plus delta Vi by Vt whole squared by factorial 2, so on. Delta Vi by Vt whole cubed by factorial 3, which is 6. So, this is the nature of variation of output. These are, I have told you earlier in a general discussion about amplifier, this is the linear term, this is the offset, this is the offset, DC offset, this is the linear term, this is the nonlinear, these are the nonlinearities. Right? We have to have these nonlinear terms made as small as possible for reducing distortion. That means delta Vi by Vt should be much less than 1. This is an important for making this common emitter transistor a good amplifier. We will discuss further in the next class.